All right, so I will begin with a word of prayer. Thanks. Heavenly Father, we thank you for this day. I thank you for these students. Just pray that you'd help us to use this time wisely, that we can wrap up any questions we still have about the course, Lord. In your name I pray, Lord Jesus. Amen. So I got you your top hat code, right? 0227. What lecture are we on?
Lost count.
Lost count? Lecture infinity? It feels like lecture... Fill in the blank, I'll put it in later. How about that? So this is solution to quiz 3. Questions about course. Again, the top hat code was 0227, right? Does anybody know what lecture it is? If not, it's really okay. Hey, listen. Let us get into the solution to quiz 3 then. If you came in late and you don't mind being on camera, your quizzes are up here, lying on the desk. You can come get them. Let's see here. So let's take a look at the solution to quiz 3 together. If I can. Did I already scan and post this? I think I did. Let me check on that. Or can you tell me? It's been a long weekend. I can't remember. I feel like I posted the solution already. Did I? If I haven't, I will. Come on, Canvas. Do your thing. Well, let's see here. Yeah, I posted the solution and a blank copy of quiz 3 in module 14. That happened. And here we go. So, where's my... So first of all, any questions about problem 1? So what goes on here is we start at A and we just pick the path which is cheapest, right? So when starting at A, you're faced with 38, 24, 15, and 27, so you pick 15. 15 takes you to C, at which point your options are 54, 34, and 49 if you want to go to a new place. So you pick 34 because it's cheapest. That takes you to E, and you want to go to a new place that you haven't gone to yet, right? So that leaves you with your choices of either B or D. B costs 42, D costs 68, so you pick B. And then at that point, you've already gone to A, C, E, and B. That forces you lastly to go to D, and then finally back to A again, and that's your Hamiltonian path. You've visited all the nodes, and yeah. So that was D. A is Roman numeral, and sure. I mean, I can try. See if I think I left my laser in the office, which is unfortunate. Or didn't I? Aha! All right, so yeah, so here we take basically the deal with the Roman numerals is you got to build the number from sums of things you're allowed to make. So with Roman numerals, it would be lovely if you could just put 4 C's like here, C, 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 C. But this is not allowed. This is an offense to Romans. Romans are like 4 C's, no, you can't do that. We only can have 3 C's, right? So that's just the rules. Don't ask me. You know, some, you know, Caesar somewhere did this. I don't know who did it. Some ancient Roman. So we're not allowed to do B. We can't put 4. So C is worth 100, right? If you put the C before the D, that makes it equal to 400 because C before D, C is smaller than D, so it's a subtraction. So the 400 is CD. The 40 is XL because L is 50 and X is 10. Whenever you put a smaller thing in front of a bigger thing, it's a subtraction. You're only allowed to do one subtraction though, right? So you can reach numbers like 4 or like 9 with subtraction, or numbers like 40 or 400 or 900 or 90. And then the 8, well, you take 5 and you add 3 to it. So this is it. So yeah, so that makes the answer A. If you are not comfortable with how to find Roman numerals, I am sorry about that. I also do not find great joy in finding Roman numerals. If you want practice, I did give you guys a website, right, that you can go back to the video with links, and you can just make up numbers and try to find the Roman numeral for it and practice that until you get it, right? And maybe you guys have a formula sheet for the final. How many? 3 front and back, right? That's certainly enough paper to write, I don't know, like 20 Roman numeral examples if you're weak on this. If you have like 20 diverse examples, then your formula sheet is very strong because, as you know, diversity is our strength. But you do have a formula sheet, so you could put a bunch of examples to help you out. Or you could try to copy the, come on. You could try to copy the algorithm from the textbook down, which I think would be less helpful. I think it's easier just to like have examples. Do you agree? Well, anyway. You agree? Yeah. Okay, I feel better now. I feel acknowledged. If you've ever watched Naruto, you know the importance of acknowledging people. It's the source of all evil in the world, you know? Let's see here. Well, at least the fictional world. But the good news is that enemies will eventually become friends. So it all works out. Not so much in the real world, though. You know? Okay, so yeah, like a week ago, I was thinking about getting like a Ye Trump bumper sticker, but then the week happened, and I'm like, people won't understand it anymore. That joke has expired. Anyway, do you guys know what the most passive-aggressive color to use in an email is for font?
Font, not color?
Yeah, like color font, like purple, red, black.
Red.
No, the most passive-aggressive font choice color is clearly white. I've put things in white in my signature before.
That's fantastic.
Yes.
Learn something new every day.
I know my audience. Let's see here. So, Euler circuit. This is not Eulerian because there are vertices of odd degree. You'd be like, well, this one also says odd degree, so this is also a right answer. But it's not a right answer because it says there are more than 2 vertices of odd degree. There are not more than 2 vertices of odd degree in this graph. There is A and there is B. Those have odd degree. But E, D, and C are all even degree. So that's why you cannot choose option C, even though it seems like on the surface of things, either C or D would be okay. It's not. The base 10 representation of the number 1, 2, 3, 4, 5, base 5 rather, is we do 1 times 5 cubed plus 2 times 5 squared plus 3 times 5 to the 1 plus 4, which gives us 194. So that direction of things is pretty easy, right? Well, it could be easy if you knew that stuff, but 5 and 6, these are, I would say they're like taking candy from the baby. But if you've ever actually tried to take candy from a baby, you know that that's not as easy as it sounds. But if you believe in that kind of saying, here it is. So what we do is we just take these different hexadecimal digits and we expand them. So like A is this 1010. B is 1011. 7 is 0111. So there's this really neat trick that we can just take each one of the digits and expand it as its binary representation. Point of order, like what's something you should have on your formula sheet? Yeah, like one of the things we should have on our formula sheet, let me just write it off right here real quick. Page 1, like something we should definitely have on our formula sheet is, octal, octal binary. How's that go? 0, 1, 2, 3, 4, 5, 6, 7. The binary is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. That's your octal to binary conversion. Oh, man. This is, oh no, we've angered it. We have angered it. All right, thank you for asking me that. I know the temptation to let me go on because it's hilarious is strong. And you who laughed are guilty of this transgression, I believe. Anyway, also hexadecimal, or hex for short, and the binary equivalent. Hexadecimal, you've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, right? So something you'd like on your formula sheet is just this table, right? And if you do it right, you can see there's a nice pattern. Like the last 3 digits are just the same as the octal one. And then it repeats. I'm getting out of order. I'll add some lines in a second here. And then, of course, you add a 0 in the front of all these ones. And add a 1 in front of all these ones. Let me put in some lines. Of course, you can make your table neater. You don't have to be in a hurry like me. But anyway, there's your hexadecimal to binary converter table, right? That would be the smart thing to have around, because then when you're trying to do a problem like this number 5, you go, okay, I've got A. So I look and I go, okay, my A is 1010. And then I've got, a B. What's B? Well, B is 1011, right? And then my 7, well, that's back up here. Up here, like 0, 1, 1, 1, 1. And then I just string those together to get that hexadecimal, get the binary representation of the hexadecimal number. And the same goes for the octal representation, right? So like to get, well, it's the other way around, right? So I give you this number. Let me stop moving it and just point at it here. See if I can get everything in place. See everything? Okay, yeah, we can see everything. So I'm trying to find the octal representation of this binary number. So what I do is I chunk it into, and I put some spaces in here to sort of give you hints. You notice I put spaces between every 3 digits to try to give you a push in the right direction. So we look at the first 3, then the next 3, then the next 3. I have to adjoin a 0 to get a grouping of 3 at the front. You can always add zeros to the left of a binary number. It doesn't change it, because that's just adding 0 times the power of 2. That doesn't change the number. Anyway, so then I look at my octal to binary chart over there, and I go, okay, 110, that's 6. 101 is 5. 100 is 4. And 011 is 3. So my octal equivalent of this binary number is 3456, base 8. Octal is base 8. If I'm talking too fast and you don't follow it, do not give up on this problem. Calmly revisit it later when you have time. You can get this one. These are not hard. Both of these, like 5 and 6, everybody can get these problems right. And I think everybody can get problem 4 right if you take a second to stop and see what's going on. It's not that bad. It's pretty straightforward. The problem that's later in the quiz is more difficult. I will grant you that. Let's look at the next page. So problem all right, so here we go. Problem 7, I was thinking about it. Given our larger conversation here, this question's not clear because I give you a triangle and I say, you have 2 angles, what's the angle of the third? In a conversation which includes non-Euclidean geometry, that's not really a clear question, because you could say, well, I don't know, because triangles can have different sums of angles, right? But if this problem is given in the context of Euclidean geometry, then we're okay, right? Because the Euclidean geometry, the sum of the angles interior to a triangle is 180. So if I've got a 21 and a 49, those add together to give you 70. And if you take 70 and subtract it from 180, you get 110. So the 110 degrees was the remaining angle there. Problem 8 is the Pythagorean theorem problem. So just kind of like draw the a squared plus x squared is equal to y squared. So we solve for a squared and then take the square root of both sides. We get square root of 16, which if you didn't know, you can put in your calculator. Anyway, it's 4. All right, so yeah. Let's see here. So I do try to keep algebra, generally speaking, out of this course, but I think this is a fair question because there was questions like this in your homework, right? And now it's exceedingly fair because you've also seen it on the quiz. So if I put this again on the final, even with different numbers, you should still be able to do it, right? This one here, if the sum of the interior angles is 170, we learned that that's characteristic of hyperbolic space. So that's a hyperbolic space. So what's the story? If the sum of the angles is less than 180, it could be hyperbolic. If the sum of the angles in the triangle is 180, it's Euclidean. If the sum of the angles in the triangle is larger than 180, that would happen in a spherical geometry or in an elliptical geometry. 107 is a prime number. It's true. Now, I'm sure some of you got this right because you guessed, right? And that's not, 50-50, right? But how can we be sure 107 is a prime number? Let's talk about an algorithm. This is something I really haven't done justice to in class yet, so let me just take a second here to try to talk to you about an algorithm for finding whether or not a number is prime, all right? Because there is a straightforward procedure for it, and here's how I think through it. So if you're given a number, let's say n, and we want to find the prime factorization of n, right? Which is multiplying numbers that are prime, which gives you back n, right? Then we can get it by successively dividing n by prime factors, possible prime factors, I really should say. To be clear here, possible. So we're dividing by candidates, right? Possible. They may or may not actually be prime factors, right? As it happens for a given number. So by possible prime factors up to these which are at most square root of n. So like here are the primes from up to 29. You've got 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. So these are the prime factors that you need to check to see if a number is prime up to what? Like this list of primes is good for checking primality up to what number? Well, if you square 29, what's it get you? Like, I don't know right offhand. Let me use my calculator here. So 29 squared, 841. So if you've got a number that is less than 840, all right, if you check if it's divisible by 3, 5, 7, 11, 13, 17, 19, 23, and 29, and none of those divide that number evenly, you can be sure that that number is prime. That's what this theorem says. So that's pretty neat. You only need to check up to the square root of the number for prime factors. After you get to that, you're done. So like 107, let me just skip ahead to 107 here, which was the problem on the quiz, right? So 107 is prime. Why is that true? It's prime because if you look at the possible prime factors, so the square root of 107 is a little bit more than 10, right? So you really only, 11 squared is 121, so that's out of the question. 11 can't be the prime factor we're looking for. there has to be something smaller that's a prime factor first. And so you only have to check 2, 3, 5, and 7. And none of those divide 107 evenly. Like you can, what do I mean by that? What I specifically mean is if we take 107 and we divide by, let's say, 7, what happens? Oops, sorry, I tried to get out of this glare there. So my handy dandy calculator here gives me back 107 over 7. It's like, thanks. That's really helpful. But what that means is that if you go to the decimal approximation, it doesn't divide it evenly. Right? In contrast, if I do like 105 divided by 7, what happens? I get 15, right? So that means 7 is a divisor of 105 because, in other words, 7 times 15 is 105. All right? So going back to my examples here, to check for prime, we just need to examine, prime factors up to the square root. So if I look at 352, if you have an even number, it's kind of easy. You pull a 2 out, right? You know that. And then that pulls out 176. Then I can pull another 2 out of 176, right? And then I can divide 88 by 2 and I get a 44 out, right? And so you just keep pulling off factors of 2 until you get something odd. And I work my way down to 2 times 2 times 2 times 2 times 2 times 11 there. So like the prime factorization of 352 is 2 to the 5th times 11. Let's see here. This one's a little more interesting. Example 2, we take 303. So that one's not even, right? So 2 is not a divisor. The next thing to check is 3. Does 3 divide 303? I think you can see it does, right? 3 times 101 is 303. So that means 3 is a divisor. Then we get to 101. Is 101 prime? How do we check? We have to check the possible prime divisors, which are what? 2, 3, 5, 7, and not 11. 11 squared is 121. That's not even a potential smallest prime divisor. So because 101 divided by 3, divided by 5, and divided by 7 are not whole numbers, that means that 101 is prime. So you actually only need to check 3 numbers divisibility to check that 101 is prime. On the surface of things, it might seem like you need to check a lot more than that, right? But you don't. That's the logic here. Here, let's try a different number just for the sake of making sure we understand each other. How about 247? Is it prime? Excuse me. I need another page. Where's the paper? I guess I'll do it this way. So consider 247. Find prime factorization. So we do what? Like 247 divided by 3, right? You can see already that 247 is not divisible by 2, right? That's out. It's not even. Yeah?
Maybe shouldn't we have done the square root?
Oh, sure. Square root of 247 is what? That's a good point. We should do the square root first. So the square root of 247 is 15.72. So that's a good idea. That means we need to check on what? We just need to check what? 2, 3, 5, 7, 11, and 13, right? So if it has a prime factor, if it has a prime factor, the smallest prime factor has to be one of these guys. All right? So 2 is out, right? Let's see here. How about 247 divided by 3? What happens with that? 247 divided by 3 is out. You see that one again gives me a 0.33. So that doesn't divide evenly. How about 247 divided by, I can do divided by 5, but you guys know that one doesn't work, right? Does not divisible by 5. How about 247 divided by 7? Well, that gives us 35 point. That one doesn't work. 247 divided by 11. That one doesn't work. Oh man, it's starting to look like it's primed, isn't it? But what's 247 divided by 13? Ooh, 19. So in fact, 247 is equal to 13 times 19. So it is not prime because it's composite, right? It's if you can find a way to multiply two numbers together such that you get the number that you're given, that number's not prime, right? This is a composite number. Its prime factors are 13 and 19. Does that make sense?
Yes. Can you go over a problem with if it's even?
If it's even, in what sense?
Like if it's an even number and you're trying to see if it's prime, that.
Yeah, so if it's even, it's not prime.
Oh.
So like if it's the only even prime is 2.
Oh, okay.
Like otherwise you can factor a 2 out, so it's not prime. So the interesting primes, they're all odd. A lot of theorems in number theory start with suppose the number's odd and then blah blah blah. Okay, hey, let me get back to quiz 3. I just wanted to say a few words about prime numbers. I know some of you guys like already have this sort of ingrained in you from like elementary school or whatever, but if you don't, this is basically an algorithm you can use to solve this kind of problem. And sorry I haven't said more about that earlier in the course. It's my own stupid fault. Oops. Sorry. One thing at a time here. Page 2. So where were we? 107 is a prime number that is true. Let's see here. If a space has a property that there's just one parallel line through a given point off the given line, the geometry is called Euclidean. That's the parallel postulate. Or maybe it's Playfair's axiom. I forget the exact name of it, but some people call that the parallel postulate. I've called it the parallel postulate in here. And then question 12, the geodesics on the sphere are known as, in fact, the answer is shockingly not the MAGA circles or the Magaga circles, but great circles. If you got this problem wrong, it's on you. So also, point of order. Some of you are leaving questions blank. Why? It's multiple choice. Is it, oh, wait a minute. Is a deep-seated feeling, you have a deep-seated conviction against gambling? That must be it. There is no reason. I do not take off points for, like if you leave it blank, you lose all the credit, right? So at least make a choice because then you're in the running, right? You might get it right. It's multiple choice. You've got a chance. Leaving it blank, you're for sure going to get it wrong, right? So now on the final, don't do this. Like choose one answer. Also, you must choose one answer. Do not choose two answers. If you choose two answers, you will also be counted wrong. It is multiple choice, not multiple choices. You must choose one answer. Please, one answer. All right, I will get off my soapbox. I'm just trying to get you guys to keep more of the points. I have enough points. I do not want more of your points. Yes? A spherical triangle of radius 2 has what? So the formula for the area of a spherical triangle was what? You add the angles in the triangle up, measure of A plus measure of B plus measure of C. You subtract 180. You multiply by pi over 180. And then you multiply by the radius squared. This is the formula that we had to use to work the problems in the WebAssign. It's in your textbook. We talked about it in the lecture. It works out to 4 pi here. So 4 pi. What is the genus of the region pictured below? So 1, 2, 3, 4 holes. It has genus 4. All right. Which of the following are topologically equivalent? So like one of the big ideas, pretty much the only big idea we had in terms of topology was we can compare two different objects. If they have the same genus, they're topologically equivalent. Now, if they have different genus, if they have different number of holes, they're not topologically equivalent. And topological is just like a fancy word for saying you can kind of smoothly deform one thing into the other without tearing it, right? So here, the mask and the scissors are both genus 2, and these are the ones that are topologically equivalent. The pretzel has genus 3. The coffee cup has genus 1 because only the ear. Did you guys call it the ear of the cup? Handle. I don't know. In my house, it's called an ear for reasons I don't understand. But the ear of the cup. Okay, fine, handle. You'll be all normal about your naming. Fine, whatever. In the lecture after Thanksgiving break, I shared some slides which showed how to produce neutrons and a host of other less known particles constructed via. The answer was tensor products of quarks. That was the wacky pictures I showed you guys in my show and tell day. Cylindrical Earth woodtronics is a different thing. That's not right. Where was I? Oh yes, the final page. Let's see here. So it is silly, but I did take off points. I did prove that I was Batman, not Superman. So, you know, stupid but true. I am Batman. So that is false. I showed I was Batman, not Superman. And we should not confuse Batman with Superman, as one of those fictional characters is lame. Let's see here. Now, Riemann, I told you guys, Riemann gave examples, in fact, many, many examples of elliptical geometry, because he introduced the concept of a manifold, and he showed how the concept of geometry could be interlaced with the concept of a manifold. He introduced what was known as curvature, which then was later used in general relativity to set up equations which describe gravity as a consequence of the curvature of space-time. Now, I was very, very lackadaisical on my grading of problem 1. If you wrote something that wasn't just something like, I don't know what to do here, almost anything I gave you credit for that, so like whatever. Problem 2, I am sorry. I told you guys that would not be on quiz 3, and then I forgot. And then one of you reminded me, hey, you said this wasn't going to be on quiz 3, and I was like, hurt me with that. It's true, I did say that, and I hate when I don't do what I say. So, of course, I just didn't grade this problem. So no points were taken off for this. You shouldn't have gotten points taken off for that. Many of you did get it right, though. So that's good, and some not so much, right? What was the deal? The hot dog is a 10,000. The lotus flowers were 1,000. The scroll was 100. And the strokes were 1, so that's how it works out. Yep. I did give you points for it. Everyone got points for it. So yeah, I just gave everybody 3 points. Yeah. So I mean, you still got the points. I just didn't. I grade negatively. I only take points off. I don't, because well, there's a variety of reasons, mostly having to do with students skipping problems. But less of an issue on these tests. But problem 3, the Euclidean distance is the square root of the sums of the squares of the differences between the points. So like, I'm going from -3 to 2, so I do 2 minus a -3, which gives me 5. And then I'm going from 4 to -14, so I get like -14 minus 4, which gives me a displacement in the y direction of -14. So 5 squared plus 18 squared is what you got here. I think that works out to 349, so the square root of 349. Some of you wrote your answer as the square root of 349, and that made me get my calculator to like look at it and go, oh, yep, they're right. So yeah, square root of 349 is also this. Now the city distance is that means that you're going just horizontally and vertically, and the formula for that is just take the absolute value of these numbers and add them together. So the absolute value of 5 plus the absolute value of -18, which gives you 23 for the city distance. So if you didn't get this right already, take a few minutes to figure it out. You can do it. It's not that bad. It really is not. Everyone can do this. Some of you are leaving your answers as like pairs of things. I don't know what that's about, but you're not alone. Like there's a few of you leaving your answers as pairs. I don't know what that's about. Problem 4 is, I think, by far the most challenging question on this quiz. Yeah. And I've done a bunch of these. So like I do think it should be on the final, something like it. But I understand it's, there's something to learn here if you haven't learned it already. Let me just go through again the logic. So here's the deal. If you've got a number and you're trying to find its base whatever representation, your first order of business is to find the largest power of your base that will fit inside the number. So if I'm working on finding a base 7 representation of a number, my first order of business is to write a list of the powers of the base to the side, just to keep track of what I'm working with, all right? Because, so like I have 1534. So I look at 7 squared, I've got 49. Okay, I can definitely fit that in there. 7 cubed is 343. Can I fit that in there? I certainly can, right? 7 to the 4th, 2,401. Well, that is bigger than my number. So that means that the first interesting digit, it's happening where? It's happening in terms of a multiple of 7 cubed. So I figure out, what can I do? How can I fit 343? So I divide 1534 by 343, and what it gives me is 4.472 dot 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 dot. So this shows me that I can fit 4 copies of 343 into this number. So I get 1534 times 4 is equal to 4 times 343 plus 162. How do I get this 162 here? I use my calculator, all right? This is gotten from 1534 minus 4 times 343. That gives me 162, all right? So the most copies of 343 I can get are 4. That's it, right? I can't get 5, I can't get 6. And then, so, okay, well, how about 162? Well, 162, I can fit 49 into that, right? And I could just kind of eyeball it and say, well, that's close to 150. So I can get 3 copies of 49 into there, and then I have to add 15. Again, this 15, so I take 162,